So in this section, we want to take a look at a very important but also very fundamental concept in mathematics, and that is the idea of functions. So let's start off with a couple of definitions, and then we'll segue into some examples. So definition, let x and y be sets. A function from x to y is a subset of the Cartesian product x cross y, such that for each x in x, so for each little x in the big set x, there is exactly one y in y. And the way that we often notate this, at least in an abstract setting, we would often simply say, my function f is a mapping, and we'll see what that means in just a second on the next slide. But this first set x right here is what we're going to call the domain of my function. And this second set right here, y, is what we sometimes call the codomain. So this function f, okay, will map or relate some numbers from some set x, the domain, to some set y, which we will call the codomain. The set y, such that xy is an element of the function, is called the range of the function, and the range is a subset of the codomain. Now, I'm sure for those of you who have had algebra before, you've probably seen this idea of domain and range before, but this idea of codomain might be a little bit new to you. Let me just introduce a very quick example to show you the difference between what I'm talking about when I say codomain and range. So let's say I have a function f from R to R. So this R right here is the set of real numbers. That is my set x. And this is what I'm calling the domain. This R right here is what I'm calling y. It is also the set of real numbers. And this is what I'm calling the codomain. So this function, though, f of x, let's say, is the function x squared. So if I think about this function f of x equaling x squared, what this is doing is it's saying the inputs come from the real numbers, okay? And the outputs, or the codomain, are also real numbers. But here's the issue, okay? The range of this function is not R. The range of this function right here is not the set of real numbers. And this is why, if you think about it, when you take a real number and square it, you never get a negative number. The range are the set of non-negative numbers, 0 up to positive infinity, if I use this idea of interval notation from an algebra class, okay? And so the codomain is the set of real numbers. That would be minus infinity to infinity. But for this specific function, the range is simply 0 to infinity. That's why the range is a subset of the codomain. Now, sometimes the range may be an equivalent set to the codomain. They may be the same thing, the same set. We may take a look at an example of a function where that is the case, but I just want to emphasize this fact that codomain and range are not necessarily the same sets. Okay, so I got functions, I've got domains, I have codomains, and so let us introduce three new definitions. So a function f mapping x to y, so the domain is x, the codomain is y, is said to be one-to-one, or some textbooks will use the word injective, if for all x and y in the domain, if f of x1 equals f of x2, then x1 equals x2. If this is the case, don't worry, we'll take a look at some examples that illustrate this in just a second. But if this is the case, then we're simply going to say that the function is one-to-one or injective. A function f mapping x to y is said to be onto y, onto the codomain, or surjective if for all y in the codomain there exists an x in the domain such that f of x equals y. If that's the case, then we say that the function is onto y, or we might call it surjective. A function f mapping x to y that is both injective and surjective, so both one-to-one and onto, is said to be bijective. This prefix bi simply meaning two. So functions that are one-to-one and onto are often called bijective functions. So let's take a look at this little example right here, this little illustration. Okay. So this first one here on the left is an injective function, or an injection function. It is one-to-one. Okay? So I have these guys over here, x, members of the domain, and these guys over here, y, in the codomain. And here's the idea. I might call this guy x1, x2, x3, x4. We'll call this y1, y2, y3, y4, y5, etc. Now, this is why this is said to be one-to-one. So take a look at this y1 in the codomain. Okay? He is relating to only one member, x1, back in the domain. Take a look at this member, y2. He is the output for only one member, x2, in the domain. Okay? And so if I take a look, that these outputs, or these y's, these little y's in y, okay, are the mappings of specific one and only one little x's in the domain. Okay. Now let's emphasize though that this first one right here, this injection, it is not onto. Why is it not onto? Well, simply there is this y4. There is this y4 in the codomain that no x maps to him. No x gets to relate to y4, and so this function is not onto y. Now, let's take a look at the one on the right, a surjection or a surjective function. So let's say I have these little x's in big X and little y's in y, and maybe I were to label them. So x1, x2, x3, x4, I'll label this y1, y2, y3. Okay. Why is this onto y? Why is this function onto y? Well, take a look. There are only 3 elements in the codomain, and every single one of them gets hit by a member in the domain. And so this function, whatever it is, this function f, is said to be onto y, because every y is getting related to by some x. Now, why is it not one-to-one? Well, this function right here, this top right here, is not one-to-one. This is y. Okay? So I had this guy right here, y3, and if I called him x3, and this guy right here, x4, this output right here in the codomain, this y3, okay, is relating to an x3 and an x4. In essence, it is the output for 2 different inputs, and so it is not one-to-one. Now, if I combine the 2 of these together, a one-to-one and onto function, I get what is called a bijection. So I have little x's in x, little y's in y. Maybe I'll call these x1, x2, x3, x4, y1, y2, y3, y4. And so if I take a look at this mapping right here for this function f, first off, each member in the codomain y, okay, is relating to only one member in the domain x. That's what makes it one-to-one. Furthermore, the function is onto because all 4 elements in the codomain get hit, meaning they have a relation to where everyone gets mapped to. So that's kind of the idea of injection, surjection, and bijection. So let's use that idea to take a look at some very basic examples. So let f map x to y, where x is the set 1, 2, 3, 4, y is the set a, b, c, d, and determine if the following are functions. Okay, so before I even jump in, okay, this x right here, the set 1, 2, 3, 4, is what we call the domain. And this set y, the set a, b, c, d, is what we call the codomain. And so f is going to map x to y. In essence, a function is simply a relation or a mapping. It relates some elements in the first set, x, the domain, to elements in another set, y, the codomain. And so I simply want to take a look at these functions, okay, and determine if any of them are one-to-one, onto, or both. So let's take a look. And one of the classic ways to take a look at a function, okay, is by what we call a mapping. So I have these numbers right here. 1 maps to C. 2 maps to A. 3 maps to B. 4 maps to C. And 2 maps to D. Okay. Well, let's take a look at this right here. My claim is from the onset that this is not even a function. The reason that this is not a function, why, is because the function evaluated at 2 outputs an A, and the function evaluated at 2 outputs a D. And the basic definition of a function means that each element X in the domain must relate to only one element Y in the codomain. So this is not a function. Okay, let's take a look at another one. So I have my X, I have my Y. Okay, so 1, 2, and 3. A, C, 1, 2, 3, 4. We'll just say A, C, B, D. And yeah, we'll just go in alphabetical order. So 1, 2, 3, 4. Okay, so 1 maps to A, 2 maps to C, and 3 maps to B. Okay, well, first off, this is a function because each element in the domain, okay, is relating to only one member in the codomain. Okay? And my claim is also that this function is one-to-one. It is an injection, okay? But not onto. The reason it's not onto is because there is this little lonesome D right here in the codomain, and notice nobody maps to him. So if we view it from that perspective, since nobody maps to or relates to this D, who is a member in the codomain, we simply say that the function is not onto Y. It's not onto the codomain. Okay, let's take a look at C. I'm going to erase these right here so we can take a look at C. So for this guy, I have my set X, I have my other set Y, 1, 2, 3, 4, A, B, C, D. Okay, and let's look at the mapping. So 1 maps to A, 2 maps to D, 3 maps to B, and 4 maps to C. So this is a function And my claim is, yes, it is 1-to-1 and is onto Y. How is it 1-to-1? Well, every member in the codomain relates to one and only one member in the domain. And why is it onto? Well, notice there are 4 elements in the codomain, A, B, C, D, and every one of them gets hit. So in essence, nobody in the codomain is feeling left out. And so we would simply say that this is onto. And so what we would formalize this is we would say that this is a bijection, a 1-to-1 and onto function. Okay, let us slide down and take a look at E and F. So over on the next page. Okay, so let's say I have a function mapping real numbers to real numbers. So my domain is the set of reals, my codomain is a set of reals, where f of x equals x cubed. Okay, for those of us who know what the graph of the x cubed function looks like, it does something very similar to this right here. Okay. This function f is 1-to-1, and it is onto y, which is the set of real numbers. And so I would sometimes say f is onto r. And so because it is 1-to-1 and onto, this function f is a bijection. Okay, what about the function mapping r to r, where f of x equals x squared? Okay, so for those of us who know what the x squared graph looks like, that is this shape, like so. Okay, so my claim is f is not one-to-one. Okay, how is that? How do I know that this function f is not 1-to-1? Well, take a look. Let's say I evaluate this function at 1. Well, that would be 1 squared, which would output a 1. And if I were to evaluate this function at -1, -1 squared also outputs a 1. So in essence, if I look at it in the form of a mapping, so x and y, and these are not the only elements in the domain and codomain, okay, but -1 maps to 1, and 1 also maps to 1. -1 squared is 1, 1 squared is also 1, and so this is not 1-to-1. The reason is because this output y, this output 1, can be obtained from -1 and +1, so it is not 1-to-1. Also, f is not onto r. Why is that? What does that mean when I say that it is not onto r? Well, what I'm simply saying right here is there's no way to get negative numbers as outputs for this function. When I square a number, it's never negative, okay? And so this function is not onto R because there's no way to get a negative number for an output. So it is not onto R. Okay, let's slide down here and take a look at this next example. So I wish to prove that this function, f of x equals 2x plus 4, is 1 to 1. And so this is a very classic, very basic proof. Okay, so proof. So let x1 and x2 be elements of the domain X, which is simply the set of real numbers R. Now, I get to assume that f evaluated at x1 equals f evaluated at x2. We now must show that this forces x1 to equal x2. So, to this end, if f of x1 equals f of x2, then 2x1 plus 4 equals 2x2 plus 4. In essence, I simply evaluated the function at x1 and then x2. If I do a little bit of algebra and arithmetic, I subtract a 4 from both sides. So 2x1 equals 2x2. And if we divide through by the 2's, then I get x1 equals x2. Thus, f is 1 to 1. So there we have it. We proved using the definition that this function is 1 to 1. Okay, let's slide to the next page. Take a look at a different definition. Let f map x to y be a bijective function that is 1 to 1 and onto. Okay, so for this function f, its domain is x and its codomain is y, and it is both 1 to 1 and onto. The function f superscript negative 1, and this is read f inverse. F inverse is the function mapping y to x. Okay, so notice, what did I do? I took the original function f and I swapped the domain with the codomain. Where f mapped x to y, f inverse maps y to x, defined by f inverse equals the set of y comma x such that x comma y is a member of the function. And this is also a bijective function, and we call it the inverse of f. Okay, so very, very basic example right here. So let's consider this function f mapping x to y. So we have 1, 2, 3, a, b, and c. So for this function f, f maps 1 to a, 2 to b, and 3 to c. And it's important to note, okay, it is important to note, okay, that this function f is a bijection. It is 1-to-1 and onto. Okay? If it's not a bijection, then that makes things very tricky when I talk about inverses. That's why we require f to be both 1-to-1 and onto. So this function f is 1-to-1 and onto. And it's important to notice that this function f maps x to y. Now, if I were to consider this function, f inverse, mapping y to x, so y and x, well, what are the members of y? A, B, C, and x, 1, 2, 3. So in the inverse, A will get mapped to 1, B will get mapped to 2, and C will get mapped to 3. Now it's also important to note that f inverse is also a bijection. This inverse function is also 1-to-1 and onto. And the big thing to simply notice is that I just interchanged x and y. I swapped the domain and the codomain. And then the other thing that we simply want to notice is that f inverse inverse equals f. Meaning if I took a look at this function right here, f inverse, and I found his inverse, so I swapped x and y yet again, I would arrive back at the original function. And so we simply say the inverse of the inverse is the original function. And so that shouldn't come as a big shocker, but it is. Okay? So let's do one more example. Okay, so let's let f map r to r plus. And so when I say r to r plus, so the domain x is r, and the codomain y is r plus. This is simply the set of positive real numbers, okay? So first, let's show that f is a bijective function. Okay, I guess it would help if I wrote down what the function is. So f of x equals 10 to the x. Okay, so prove. F is bijective. Now, we must show f is both 1-to-1 and onto r plus. Okay, so let's first show 1-to-1-ness. So let x1, x2 be in the domain, and assume that f of x1 equals f of x2. We must show that x1 equals x2. So to this end, ten to the x1, I guess I'll write it like this. I get to assume that f of x1 equals f of x2, which would imply 10 to the x1 equals 10 to the x2. Okay, well, view it like this. If 10 to the x1 equals 10 to the x2, and I get to assume that that's true, if the bases are the same, then the exponents have to be the same. So this happens if and only if x1 equals x2. Thus, f is 1 to 1. We now show that f is onto r plus. So, let y be a member of the codomain, r plus. Then, there exists an x in the domain, a little x in R, such that f of x equals y. That is 10 to the x equals y. Thus, f is onto r plus. Hence, f is a bijection, or a bijective function, simply both 1 to 1 and onto. Okay, so now that part A is done, we've showed that this is a bijective function. We want to pivot and find the inverse function f inverse. So let me erase this and we'll scroll down and find the inverse. So we now want to find the inverse function. Okay, so we now find f inverse for f of x equaling 10 to the x. And how do we know such an inverse exists? Well, we know because f is a bijective function. Because it's both 1 to 1 and onto, it's going to have an inverse function. So, since f is bijective, f inverse exists. So, let's let y equal 10 to the x. Now, if f maps x to y, then f inverse will map y to x. So, interchanging x and y gives x equals 10 to the y. Solving for y gives y equals logarithm base 10 of x, or simply y equals logarithm x. So f inverse equals logarithm x. And so that's the inverse for my function. Okay, so that will conclude our lesson on functions.